Okay, let's get started. So let's briefly recap the things that we were discussing last time. So we are basically discussing the idea of the NERF, and I also know that you implemented the NERF in the assignment too. So you might have some now the basic idea about the NERF, which was the case that we are basically reconstructing the all the 3D from the multi-view images without having any kind of supervision. So this was actually not a kind of some neural net training kind of things. It's basically the things that we are kind of like trained in neural net, but it's not any kind of some sort of the supervised the learning kind of the pipeline. We are basically doing actually some kind of the optimization in terms of that only for the 3D scene or the objects that we are having the multi-viewed images, we are getting some kind of the reconstruction for the multi-viewed images. And for that, we basically have some kind of a neural network, which is basically predicting the two quantities. One was basically the opacity, which is basically the position-dependent quantity. So for every single point in the 3D space, we are basically getting this kind of the opacity information. And the other one is basically the radiance information, which is like position and also the view-dependent quantity. So given the point and also the view direction, we are basically getting the color information. So those are basically the two quantities that we are predicting. It's kind of using some the implicit function that we are basically learning using the neural network. And the basic idea of the NERF is basically leveraging this kind of the volume, the rendering the equation. So this was basically not some kind of the random kind of idea in terms of like getting the images from each of the view, but actually we are shooting the rays from each of the view for every single pixel, and then for each of the ray, we are sampling the points over 3D space and collecting this kind of information. Basically, the opacity and the radiance information along all the samples that we are sampling for each of the ray. And based on that, we are basically calculating the final color information like this. And for that, basically, the interesting thing was that we are basically somehow leveraging some kind of physical properties to calculate all the color information. So actually, the quantity that we are calling as the opacity was also called the extinction coefficient, which is basically precisely defined as kind of the differential probability of like how likely the ray will stop at the point. So what we are seeing in this kind of null pipeline was that we are basically shooting the array for each of the pixel and having some multiple samples along each of the array. And for each of the sample, we are actually calculating the probability of like how likely the array will stop at each of the point. So that was basically the quantity that we are calling as the extinction coefficient. But actually, this was precisely differential probability, which means that the final probability is actually calculated by multiplying the delta t, the infinitesimal length for each of the interval of the samples. So if you basically multiply the opacity value, multiply by basically the infinitesimal length for the interval of the samples, that becomes the final probability of like how likely the ray will stop. The ray will basically hit a particle at that point. And the transparency was actually a quantity that is basically computed based on the opacity value. So the transparency, the meaning of that was basically we are also calculating probability of like how likely the ray will travel until that point without basically hitting any of the particles. So based on this kind of the definition, we can see that actually the transparency can be computed based on the extinction coefficient. So it's actually quite obvious to see that the transparency after t plus the delta t, the distance, can be actually computed by basically this quantity. Basically, this quantity means that we are basically seeing how likely the ray will traverse until the point of the time t, and also it does not basically hit any kind of the particles inside this kind of the some small kind of the delta t length. So if the ray travels until the time t, here, let me rewrite here, okay? So if the ray basically travels until the time t, and also it does not hit any kind of the particles, during the delta t here, then we can see that the multiplication like these two probability becomes the transparency, that basically the t plus delta t, that basically indicates the ray also travels until the time of the t plus delta t. And so we can see that it's actually this is kind of the ODE formulation, especially when the delta t is basically converted to 0. This will be basically the ODE formulation. And if we solve the ODE formulation, then we end up getting this kind of the final D equation. So this becomes the final the transparency, the equation in the continuously setup. So the good thing of like using this kind of equation is that this is basically not having any kind of the random weights. So what we can actually see is that, so in the previous slide here, yeah. So we can actually see that the multiplication of the transparency and the opacity, these two can be actually considered as kind of the weights for each of the kind of the radiance value. So you can see that actually this is kind of nothing but basically taking some the weighted sum of the radiance to basically determine the color of each of the pixel. But when you basically compute the weights for each of the sample, the points, we are basically not just directly, predicting this kind of the weighted value, but actually these kind of the weights are basically calculated as kind of the multiplication of the transparency and the opacity. And these two are basically having some kind of physical meaning. In terms of like one important thing is that this transparency function becomes the non-inclusive function, right? So if we see the definition of the transparency in the previous slide here, this is basically taking the integral of some kind of the non-negative value, which is the opacity here, and taking the minus of the exponential here, right? So this basically becomes the function, which basically is non-increasing function. So as you basically go further and further, the transparency never increase, right? It always basically, it can be the same or it can decrease, right? And it makes sense. As we basically go further and further, the probability that the ray will basically travel until that point cannot be increased, right? So this is basically following the physical concept in terms of that the transparency becomes the non-increasing function. So in this way, basically by incorporating this kind of the physical idea, we can make the neural net training becomes like more stable and can convert this like the faster. So that's kind of the idea of like using this kind of the volumetric, the volume rendering the equation in the neural reconstruction. But also one thing is that these are all the cases that when you have some kind of the all this equation in the continuous setup, the things that we need to also discretize everything in our computation. So what we can do in the real NeRT implementation that you already implemented in the assignment 2 is basically using this kind of the stratified sampling, which basically means that we are having some kind of the uniform intervals along each of the ray. And randomly sampling any of the points inside of each of the interval here in a way that we can basically get some kind of the opacity, the information for each of the sample here. And we are assuming that the opacity value that we are getting from each of the point here is the kind of the opacity, the constant opacity over the entire this kind of the interval that basically include the sample. This is the simple idea, right? So what we are going to do is that we are basically taking the uniform interval along each of the ray, and for each of the bin of the intervals, we are basically sampling, like randomly sampling any point. And once we get the opacity value for this point, we assume that the opacity that we are getting from the sample is the constant opacity over the entire this specific bin. So that's the basic idea. So basically, based on that, what we can do is that once we basically get the opacity value, the constant opacity for each of the bin, based on that, we can actually calculate the transparency until the end of each of the bin. So if I just draw this again, like this. Yeah, so if we have like this one, like multiple bins, then once we basically sample any kind of the points for each of the bin, we calculate, we basically predict the opacity for each of the samples. And based on that, we are basically calculating the transparency until the end of each of the bin here, which can be basically directly computed by just taking the sum like this, because now we are assuming that the opacity is basically the constant over each of the bin, right? And based on this information, now we can also calculate the volume rendering the equation that we have seen in the previous slide. But here, basically, what we can do first is that we can think like So let me clear this. So we are basically, what we are doing in the volumetric D equation is that we are taking the integral of this quantity here over the entire range of the array, right? From the time 0 to the time capital T, for example. But let's think about the case that we are taking the integral for each of the bin as well. So this is the case that we are taking the integral for each of the bin. And what we can do is that actually, while we are basically assuming that the opacity is basically constant for each of the bin, actually we don't need to also assume that the transparency is also the constant because the transparency is basically the quantity that we are getting as kind of the integral of the opacity. Actually, we don't need to assume that the transparency is also the constant, but we're actually calculating some continuous quantity of the transparency for each of the bin for some kind of the better approximation. So what we can do is that while we are taking the integral for this specific bin here, still the transparency here should be computed based on the information from the previous bins, right? Because the transparency is basically quantity, which is also defined based on the opacity of all the previous bins. So what we can do is that we are basically splitting the range of like from the 0 to the t, the time t here, to these two the range. So when you basically take the integral from the 0 to the t, we are taking the split of these two range from the range from the 0 to the starting point of the range, the bin here, ti here, and also the range of the rest of this, like ti to the t. So what we are seeing here is that, let me clear this again. Yeah, then what we are seeing here is that, let's say we are having the multiple bins here, like this. And then now we are computing this quantity for these specific bins. And then for each of the time t here, what we do is that we calculate the transparency for, let me change the color like this. It's not working on my. So we are basically calculating the transparency in this range first, which are basically computed based on the constant opacity for each of the previous bins, and also computing the transparency for the rest of the range like this. So the first part, this integral becomes this one, and the integral for the rest of the part becomes this one. Right? So by basically splitting these two range, we can basically calculate all this equation. Basically, the transparency of until the previous bins can be pre-computed as the Ti in the formulation in the previous slide. And we can also compute the transparency for the rest of the parts using the same equation. So what we get, and we are getting, and at the end is basically this equation. So yeah, you can basically calculate all these kind of things, and then we can see that, and at the end we are basically getting this equation, and we can see that basically this is the kind of the probability, or like how likely the array will stop for each of the time t here, which becomes kind of the weight for each of the radians. And then what we can do is that since this was basically integral for each of the bin, so let me go back to the previous slide. So while we are basically computing the transparency using all the information in the previous bins, this was the case that we are basically calculating the integral for each of the bin, which means that we need to basically accumulate all this kind of information that we computed for each of the bin. So if we basically sum up all this equation, the quantity that we define for each of the bin over the entire set of the bins, then we can get the final color information. So that becomes the final color information for each of the pixel. So this was basically the idea in terms of like how we can calculate all these quantities by having some kind of the discretized samples along each of the array. So this was basically the formulation that you implemented in the assignment 2. And I strongly recommend you to basically check out all the details in terms of like how exactly this formulation was derived. Actually, depending on some kind of the details in this formulation, you can get some quite different the outputs. And then at the end, like what we are basically doing is that we are basically making the MLP in terms of that when you have the location, the information here, and also the view direction information. Based on this information, we are getting the opacity here, and also the color information here. And we are also having some kind of the additional kind of the component here. Then you can, I guess. So what we basically, sorry, the meaning of this kind of the extra the components here, that also we discussed that we discussed in the previous lectures. Can you guess what's the meaning of like this kind of the green components here in the NLP? So we are basically having this kind of gamma function, which is taking each of the location and the view direction as the input. And this is basically, the position and the encoding. And the reason that why we are having the position encoding is that we want to basically get some kind of the high frequency function given the input of the location and the view direction. So that is the basic idea. And you can also see that the structure is kind of interesting in terms of that basically the dimension that we are mapping each of the input to some kind of some high dimensional space is basically different for the location and the view direction. So for the location, the input is mapped to the 60-dimensional output, while for the view direction, the input is mapped to the 24-dimensional outputs, right? So this is like the one difference. And the other difference is that the location is basically fed from the very beginning of the neural network, while the view direction is basically fed at the very end of the neural network. And can you see like why we are making this kind of design of the neural network? So basically, there are two things. The first thing is that the dimension, the output dimension of the positional encoding is different, right? And the second thing is that basically the point that we are basically feeding all this kind of input is different, right? So the location is basically fed from the very beginning of the neural network, while the view direction is fed at the very end of the neural network, right? And can you see like why we are making this kind of the design? Any guess? Question 2. Yeah, so basically what we are aiming here is that we are basically mapping the position to the high dimensional space and also process that with the deeper network, which basically means that we want to learn some kind of the high frequency function. So that's basically what we also discussed in the position encoding, right? So basically, as we map the input, the high dimensional the space, and also process that with the deeper network, it becomes much easier to learn some kind of the high frequency function, which means that we are expecting that there might be some kind of the more the fluctuation of the kind of the output the quantities. And this can be kind of the true for many kind of the cases. If we have some kind of some complex shapes, depending on where you pick the sample points here, sorry, my iPad is not working. So yeah, along each of the even the array, like depending on whether you sample the point here and the here, probably like this might be the points that are basically inside of the object, while the other points, which is actually not far from the other points, is actually the outside of the shape, which means that the opacity value that we are getting should be basically very different, even when the input points are very close to each other. So this might be the case that we want to learn some kind of the high frequency function. And that's why we are basically mapping the position the values from the very beginning, and also basically processing that with the deeper network. But for the radiance, basically what we expect to see is that like for the radiance, like especially for the with respect to the view direction, even when we basically change the view direction, we may not want to see some kind of the dramatic change of the color, right? So typically for most of the cases, if we just change the view direction of the like for the object, then we might also see some kind of the color changes, but they may not be the case that we're changing the color from the, for example, like yellow to kind of the pink, right? So it might be kind of the brighter the yellow or the darker yellow, but it may not be the case that we are basically changing the color from the yellow to the red to the pink or something, right? So which means that this might be like much the smoother function. So the radiance might be much smoother function with respect to the view direction. And that's why we want to basically process the view direction with the shallow the network and also map this into the lower dimensional space in the positional encoding in a way that we can more easily learn some kind of the smoother functions for the radiance function. So that's the basic idea. Yeah. So does it make sense? So that's kind of some reasoning for the design of the NeRF, the MLPD architecture. So, and depending on some kind of the changes of the architecture, actually, you can see some kind of the different results. So I also recommend you to basically play with some kind of the changes of the MLPD architectures and see how much it also affects the final outputs. And one more thing is that also the kind of some details in the implementation that actually you may not implement it in the assignment 2. So this was basically the part that was not included in the assignment 2, which was basically the hierarchical sampling. This is kind of some idea that we can also further improve the quality of the outputs, which is basically having the two-step of the sampling. So the first idea is that we are basically uniformly sampling all the points along the array using the stratified sampling, and then computing the probability, which is basically the transparency multiplied by the opacity, right? So we are basically computing this kind of the probability, which will indicate like how likely the array will stop each of the points in some kind of the coarse network. And then we are making another neural net, which is now taking the more samples. And then now these samples are basically adaptively sampled based on the probability that we are getting from the first stage. So based on the probability that we are getting from the NeRF rendering, now we are getting some kind of the adaptive samples based on the probability values, and also computing the same thing using the volume rendering equation. So basically, by having this kind of the two sampling steps, we can further improve the final rendering the qualities. So this is also kind of the one interesting idea in terms of that we can basically achieve some better results in the NeRF reconstruction. Any questions on this? So these are some of the outputs of the NeRF. So these are like all the basic idea of the NeRF. And before you go into some kind of advanced ideas, so like improving all the NeRF, I strongly recommend you to check out all the details of this kind of the base work, so that you can have some kind of the better understanding when you also see some kind of the advanced the method. So that's basically what we discussed last time. And obviously the NeRF has lots of kind of the limitations as well. So for most of the cases, basically the NeRF requires to basically have some very accurate camera information. So if the camera pose information is not accurate, then we cannot also get some good reconstruction quality. So there are also some kind of the list of the work that tries to address this kind of the sort of the limitation of the NeRF that requires the accurate camera information. And also, the NeRF is basically is only working for some kind of the static scenes. So if we have some kind of the moving objects or some kind of having the dynamic scenes, the vanilla NeRF architecture cannot handle this kind of the cases. So there are also some kind of the variants that tries to basically handle this kind of the dynamic objects in the scene. And also the NeRF can handle some kind of the cases like changing the lighting. So there are also some kind of line of the work that tries to basically allow some kind of the editing of the lighting. And NeRF is also not giving some kind of precise geometry information. The only information that we are getting is basically how likely the ray will stop for each of the points. So that is kind of giving some sort of the geometry information, but not the precise geometry information. So there are also some kind of the advanced work that focuses on basically getting some more precise geometry information from the NeRF reconstruction. And also, as I said, NeRF is basically just running the optimization for each of the scene. So it's basically not something that we are doing some sort of the supervised learning in terms of that we are training the neural net from some set of the data and basically generalize this information to the other kind of the data. So we are not doing this kind of things for the NeRF. But there are also some kind of the attempts to basically generalize some kind of the information that we learn from some specific scenes into the unseen scenes. So this is kind of the idea, which is also related to the kind of this generation. So these days, like people are also talking a lot about some kind of the generative AI techniques. And from the next week, we are also going to see some kind of the ideas in terms of like how we can also extend this kind of the NeRF idea, not only for the reconstruction, but also for the degeneration as well. Basically, generating some kind of the unseen the objects. So there might be also kind of things that we're going to discuss from the next week. Any questions on this? Yeah, and actually also one kind of the big limitation of the NeRF is that as also we also discussed last time, it's basically taking lots of time, both for the optimization and the rendering. So basically for the optimization, basically when you train the neural network, it basically takes some time. Actually, you might also experience the kind of the computation time for the NeRF when you basically do the assignment too. It will take some kind of the several the hours. So as the scene is the bigger, it can take more than some kind of the hours. And the reason for that is that basically we are encoding the entire scene into basically a single DMLP, which means that if we basically want to update the information for every single point in the 3D space, then all the parameters, the MLP should be updated. So this is kind of like very inefficient kind of the architecture in terms of that, like all these set of the parameters are basically governing the entire scene in terms of that, like, every basically the point in the 3D space is basically associated with all the entire set of the parameters. So that becomes the optimization becomes like very slow. So that's kind of one of the problems in terms of like having the slow speed in the optimization. And the second problem is that not only for the optimization, but also for the rendering, it takes lots of the time because it's not just kind of doing some kind of the ray tracing. So when you basically shoot the ray for each of the pixel, once you basically sample the points for each of the ray, we also basically need to run the forward process of the neural net in terms of getting the opacity and the radius values. So which means that we need to run the forward process of neural net lots of the time. So if you calculate, basically, if you basically render a 800 by any 800 the resolution of the image, then you can see that you need to basically run the forward process more than 1 million times of the neural net. So it will basically take some lots of the time to basically draw a single image from the one specific view. So there are some kind of the ideas in terms of like how we can boost up this kind of the computation for the rendering, and also the idea for those kind of the things like boosting up all this kind of the computation is basically the idea in terms of like leveraging some kind of the other representations of the 3D data. So today we are going to get back to the kind of discussion in terms of like what would be some kind of the other representations for the 3D can be also used for the kind of the NeRF the optimization. So the first idea is basically the Plano cells. This is actually quite interesting case in terms of that now we are also running the NeRF without the neural net. So how we can also run the NeRF without the neural net. So that's kind of the interesting idea. And this is also the case that we are basically revisiting the voxel representation. So let's think about the case that now we are having the voxel representation and no impulsive function, and we are only having this like 512 the resolution of this kind of 3D voxels. And it turns out that if we start to utilize this kind of voxel representation, then the NeRF training, the optimization becomes like super fast. So the images that you are seeing here are basically results with the one epoch of the optimization, which just took the less than 2 minutes. And even with the training with the less than 2 minutes, you can see that the quality of the output is quite good, right? So these are basically the outputs that were basically trained using the Planox of the architectures. And let's see the video here. So these are basically some kind of the real-time results that we are getting when you train both the NeRF and the Planox cells. And as you can see, as we go training like over and over, the NeRF starts to get some outputs after taking some kind of the minutes. But for the Planox of the cases, even for very, from the very beginning steps, we can already start to see some kind of the good outputs. So yeah, we can get this kind of the very fast speed of the optimization when you utilize the voxel representation, not the single DMLP encoding the entire scene. So for that, basically the idea is kind of quite straightforward in terms of that. So we are going to go over some kind of the high level ideas for some kind of the cases that we are using some kind of the other representations for the NeRF training. So basically the idea of the Planox cell is that it's basically nothing but basically we are having this kind of the 3D grids. And for each of the corner points, for each of the voxels, basically we are encoding the opacity values. then what we can do is that we can basically when we sample the points along each of the array, we are first basically locating the voxel that contains for each of the sample the point, and we are basically interpolating the opacity values from the corner points in a way that we can basically determine the opacity for each of the sample the points. And then the rest of the step is basically exactly the same. We are basically using the same Boolean equation and getting some kind of the output images. And turns out actually it works quite well. And also the thing is that since all these kind of the opacity values are basically directly encoded for each of the corner points, the optimization becomes like way faster than training the NLP. Then here the question might be is that we can see then how we can encode the opacity values, but how about the radiance? The thing is that the radiance was basically not a kind of the scalar value for each of the corner points, but actually it was kind of some sort of the function with respect to the view direction, right? So if we see the radiance for each of the corner points for each of the boxes here, this should be actually not a scalar value, but it should be actually some kind of the function defined with respect to the view direction. So actually, since the radiance is basically the function of the view direction, we can actually see that it's actually the function over the unit sphere, right? Because like every single point over the sphere will basically indicate the view direction, right? So here the question is that how we can encode this kind of the radiance, the function information over each of the corner points of the 3D grid. And actually the problem might be is that how we can basically discretize this kind of the radiance function, right? So what would be kind of the way that we can discretize the radiance function in this case? Do you have any ideas here? Any idea that how we can discretize the radiance function here? Yeah, actually, if we think about like what we are doing in the spatial domain for the opacity, for the opacity, what we are doing in the 3D space is that we are just like dividing space into some multiple small pieces, which is the voxels, and they basically define the quantities for each of the sample the points, right? So actually, the idea, very straightforward idea that we can somehow discretize the radiance function might be is that we can also basically sample over the sphere, right? Actually, we can take the samples over the sphere, taking multiple samples, and when you have some kind of any arbitrary point as the view direction, we can take some kind of the nearest neighbors and take some kind of the average of this kind of quantities, right? So we can do the same thing. So this will be kind of the most straightforward idea in terms of that we are sampling points over the sphere, and that's encoding all the radiance values for each of the points. And if we get any kind of the arbitrary point, the view direction defined as the kind of the point over the sphere, then we can take some kind of the neighborly points of the samples and taking the average. Basically the same idea that we are doing for the opacity, right? So we can actually do that. So this can be kind of the straightforward way that we are basically discretizing the radiance function. But here, as we can see in the previous, the MLPD architecture of the NeRF, basically the thing is that the radiance function might be basically a very smooth function, right? So we can assume that the radiance value is basically not fluctuating that much over the sphere. They're basically having this kind of the smooth function that the value is basically not changing that much. So when you basically have this kind of the continuous and the smooth function over the sphere, what would be the other way? What would be actually the best way to approximate this kind of continuous function with the fixed discrete set of the parameters? So we are going to briefly see the idea for that. So these are basically all the ideas that we can basically discuss in the signal processing, but we are also not gonna get into all the details there. So if you are already familiar with the Fourier transform, this might be very straightforward kind of things. But if you're the first time to see the Fourier transform, we're gonna get into the basic idea for the Fourier transform. By the way, how many of you are familiar with the Fourier transform here? Raise your hand if you can click the raise your hand the button in the Zoom. Is everyone familiar with the radiance, the Fourier transform? Yes, no? Yeah, so if you are not familiar with the Fourier transform, we're gonna say the very basic idea of the Fourier transform. If you are already familiar with that, you can actually skip all this kind of part. So basically, this is very brief introduction for the Fourier transform. But the idea of the Fourier transform is that we can basically represent any kind of the continuous function as the weighted sum of the basis function, right? So that's the basic idea. So typically, the basis function that we are using for the Fourier transform is basically the cosine function and the sine function, while basically varying the frequency, as you can see here, while varying the frequency of the cosine and the sine function, we are representing all the functions as kind of some linear combination of this kind of the basis function. So that's the basic idea. So in this case, we are having these cosine and the sine functions as the base functions, and we are basically taking the some coefficients, the weights for each of the basis function in a way that we are making some kind of linear combination is the final output. So what we can see is that when we have this kind of some arbitrary function, let's assume that now we want to basically approximate this kind of the square the signal function using the Fourier series. Then what we can do is that we can take some kind of the weighted sum of that. So this is the case that we are approximating this green the line here. Yeah, so you can see that the green line here. So we are approximating the given the square function using only the first the basis function by scaling the basis function. Then this might be kind of the best way that we can approximate the given function. But as we have some kind of the more the basis function, we can get some kind of the better reconstructing the outputs like this. So these are the cases that we are reconstructing the given function with the combination of the 5 basis function. And as we have some more basis function like this, you can see that we can get some kind of the better approximation like this. Makes sense? So yeah, so as we have some kind of the increase the number of the basis function, then even for this kind of the non-smooth function, like having this scalar function, we can get some kind of the quite good the approximation results like this. So it turns out actually what we can say is that when we basically have this kind of some function like this, the same function actually can be represented as kind of the set of the coefficients of the basis function. So there can be actually 2 ways to basically discretize the given the function. The one way is that we are basically sampling over the domain of the function like this, and then encoding all the values for those kind of sample the values, sample the points. So these are basically the ideas that we discussed in the previous slide. And instead of that, what we can also do is that we can sample the basis functions. So actually, we can have some kind of infinite number of the basis functions. As you can see, we are now defining the basis functions with as the cosine and the sine functions with the arbitrary frequency, which means that we can also sample the basis functions by sampling the frequency, right? And for each of the basis function, we can take the coefficients to basically compute the linear combination. So the other way that we can basically represent the given the function with basically discrete way is that we are sampling the basis functions and also encoding the coefficients, storing the coefficient information for each of the basis function. So that can be another way that we can approximate the given function, right? And also what you can see is that for most of the cases, the good thing of this kind of the Fourier transform is that if we represent the same function as kind of the set of the coefficients of the basis function, then actually typically for most of the cases, the coefficients of the low frequency function has the higher the weights, while the coefficients of the high frequency functions have some much lower the kind of the weights, which means that for most of the cases, even when you use the subset of the basis functions with the low frequency, we can get some kind of the quite good results of the approximation. So that's the only basic idea of the Fourier transform. That makes sense. So this is also another example that we are seeing that when you have this kind of the function in the spatial domain, one way that we can represent this kind of function in the discrete way is that we are sampling the points along each of the domain and basically encoding the values of the functions for the samples. But the other way around, we can also approximate the same function is that now we are basically representing the function as the linear combination of the basis function. And then now, encoding basically, recording basically the coefficients of each of the basis function. Then what we typically see is that the coefficients of the low frequency function is much higher than the coefficients of the higher frequency functions, which means that for most of the cases, we can approximate the input function only with some kind of set of the low frequency function. So especially when the input function is the smooth function, not having the high frequency pulse, then it becomes much easier to approximate the input function with a subset of the low frequency function. So that's the very basic idea for the Fourier transform. And the same idea can be applied not only for the functions in the one-dimensional space, but also in the two-dimensional for the arbitrary dimensional space. So actually, we have seen that in the slide here. So let me go back here. So in this slide, actually, we have seen the example that we are approximating, and also here, we are approximating the scale the function, scale the signal function with the as kind of the set of the basis function. So these are basically the second row here is basically the results that we are now representing the scale the function as the coefficients of the basis the functions, right? And can you do the same thing for the 2D case as well? So now we are having this scale the function not in the 1D space, but in the 2D space like this. Then we're gonna also have kind of the basis functions in the two-dimensional space with some kind of frequency along the x-axis and also the y-axis. Then if we basically convert the scale function in the 2D the spatial domain into the frequency in the two-dimensional space, then what will be kind of the outputs that we're gonna see? Can you guess? So in the frequency domain, what we can basically assume is that for each of the pixel, which are the points in the two-dimensional space, will be basically associated with the basis function of the frequency. And as you can see, as the point goes far from the center to the outside, we are basically increasing the frequency along this direction. So if you are basically having the point here, then this point is basically associated with the one basis function that has basically high frequency along the y-axis and also some kind of the frequency with the x-axis, right? So which means that the point at the center will be associated with the basis function that has the lowest frequency both along the x and the y-axis, right? So you can basically assume that each of the point here is basically associated with some kind of the two-dimensional basis function. So what we could see in the 1D discrete case is that basically we could see this kind of the outputs. So for the 1D case, that we are seeing the peak at the center and having some kind of the ringing kind of the outputs for some rest of the part, right? In the 1D case. So in the 2D case, what we can also see is that we are seeing some same kind of the outputs. We are seeing some kind of the peak at the center like this. We are seeing some kind of some ringing the outputs along each of the axes. So this is kind of like something that we can expect to see because actually we could see the same thing for the one-dimensional space. Makes sense? And actually also one kind of interesting thing is that for the Fourier transform, there are some kind of the symmetry the properties, which means that Now, if the function in the spatial domain had this kind of the input, having some kind of some ringing kind of the effects like this, then what we can see in the frequency domain is that we are actually seeing this kind of the outputs. So you can actually see that these two are basically have some kind of symmetric properties, which means that if you are having the circle function as the spatial domain, then you're going to see some kind of some ringing the output in the frequency domain. And you are also seeing this kind of some ringing the function as the input in the spatial domain. Then we are also seeing this kind of circle function in the frequency domain. So having this kind of some sort of the frequency, the symmetry, the properties. How about this case? Now we are having this kind of the scalar function along only the x-axis, not the y-axis. Then we're gonna also see the outputs like this. So this is basically nothing but we are basically seeing the same output of like this case along only the x-axis, right? Having some kind of the peak at the center and having some sort of the ringing effect along only the x-axis. Yeah, so here the basic idea is that for any kind of the function which is defined either in the 1D, 2D, any dimensional space, well, we can basically represent all the function as kind of the linear combination of the some basis function. So even for the images like this, for this kind of gray image, we can represent all to basically transforming the function defined over the 2D space, which basically represent this kind of 2D image, with transforming this into the coefficients of the basis function in the two-dimensional space, and that will be basically transformed like this. And also here the key thing is that, as you can see, we can see that the coefficients at the center, which is basically associated with the lower the frequency the basis functions, have the higher the frequency, which means that even when you basically throw out some of the information at the high frequency like this, and then when you convert this back to the spatial domain, we can almost perfectly recover the entire function. So that's the basic idea of the compression. Actually, all the kind of the data, like the images and the audio, are basically compressed in this way. In terms of we are first like sending all this information into the frequency domain, and then basically remove all the information with the high frequency. Then the thing is that we only need to encode the information in this region, in the circle, right? We don't need to record the information outside of this circle. But even with the frequency, the coefficients with the low frequency the basis in this kind of inside the region, when we recover this back to the spatial domain, we can almost perfectly recover the input the function. So that's the basic idea of basically some kind of some compression and with some kind of the approximation with the low frequency the basis function. So see the change from this slide and this slide. So this is basically the input image here. That you can see that we are basically having this input image. And once we basically map this into the spectral domain, into the frequency domain, we are only taking the information of the low frequency, the basis function, and recovering this back to the spatial domain. And you can see that the difference with the reconstruct image on the left-hand side and the input image here is not making any kind of the big difference. See? So this is the very basic idea of the Fourier transform. Obviously, we don't have time to discuss all the details here. If you are more interested in this kind of idea, then you might also need to take the signal processing the course. But actually, what we are going to discuss is that actually we can do the same thing for the radiance function, right? If we go back to the previous case here, actually what we wanted to do was that basically we are also wanting to basically approximate the function, which is now defined not only Euclidean the 1D and the 2D space, but actually defined over the unit sphere in the 3-dimensional space. So here the question is that how we can do the same thing, some kind of the Fourier transform is some kind of the function defined over the sphere. So for that, what we need to do is that we first need to get some kind of the basis function defined over the unit sphere, right? So that's the basic idea of the Spickel harmonics that we are going to discuss in this slide. So here, all the idea is that the things that we want to do is like how we can basically achieve the same thing like the Fourier series for the functions defined over the sphere. And for that, basically, we need to first define some kind of the basis function defined over the sphere. So that's basically that basis function that we are going to use is basically called the Spicklety harmonics. And we are not going to get into all the details of the Spicklety harmonics because it takes also lots of time to discuss all the things. But very basic thing that we can basically see is that how we can basically get the basis functions for the Fourier transform. So if we see the properties of the cosine and the sine functions that we are using as kind of the basis function in the Euclidean domain, actually we can see that these are some kind of the eigen the functions of the Laplacian the operator. So in the one-dimensional space, the Laplacian the operator is basically nothing but taking the second derivatives of the functions, right? And what is the meaning of the eigen functions? I guess everyone knows the meaning of the eigen vectors, right? So the eigenfunctions basically means that when you take the second derivatives, taking some kind of Laplacian the operator for each of the space, the output of the second derivatives also becomes the same function multiplied by some kind of scalar values. So that's kind of the some cases that we are getting some kind of the eigen functions. So for example, let's see the cosine and the sine functions in the one-dimensional space. So if you take the second derivatives of the cosine and the sine the functions, and what do you get? The next question. So if you take the second derivatives of the cosine and the sine the function, then what do you get in the one-dimensional space? Well, I mean, this is really some high school things, right? I mean, these will be the things that we're gonna get as the second derivative function, right? So we are having the frequency value here. So if you take the second derivatives of each of the cosine and the sine the function, then we're gonna see that actually the second derivatives becomes the same function multiplied by some kind of the scalar values. And the scalar values is also related to the frequency value, right? So if you see actually, so if the operation was actually not just kind of operation, but a kind of the matrix, and this will be the same case that we are computing the eigenvectors, right? So eigenvectors are also defined as kind of like this kind of the case, right? For any kind of the given the matrix dA, if we can find a set of the vectors that satisfy this condition, when you multiply this vector with the matrix, if the output becomes the same vector multiplied by the scalar value, that's the eigenvectors, right? And also this value becomes the eigen values. And now we are having this finding some same cases for some kind of the operator. So this is the case that we are finding some eigen functions for the second derivatives functions in the one-dimensional case. Then we can see that actually cosine and the sine functions becomes the eigen functions, and you can see that the also eigenvalues becomes associated with the frequency values, right? So for any kind of the cases, if we can define this kind of the Laplacian the operator, we can basically find the basis function for the Fourier series by finding the eigen functions of the Laplacian the operator. So that's the very high level the idea in terms of like how we can find the basis function for any kind of some cases. So actually one of the off-topic thing is that even we can define this kind of the eigen functions not only for the Euclidean space and also the sphere, but actually for any kind of the arbitrary surface. So we are also actually discussing some kind of the 3D shape things in our course. But actually when you talk about some 3D shapes, actually we can think that the 3D shape that we are dealing with in some kind of many kind of cases can be data, but also the 3D surface can be domain for the other types of the data, right? For example, like if we are having some kind of I don't know, like some kind of this kind of human body shape, that we might basically encode some kind of some texture information or some material information or some kind of some semantic annotation. So we can see that these are actually all some kind of the functions defined over the 3D surface, right? So then even for those kind of functions that are defined over some kind of any kind of arbitrary 3D surface, basically the surface defined over in the 3D space, we can define the Laplacian operator specific to the given the shape like this, and also find the identity functions. And we can also do the same the Fourier transform, finding the Fourier space for the functions defined on the arbitrary the manifold over the 3D space. So there are lots of kind of the machineries in terms of like how we can do this kind of Fourier transform for the functions defined over the 3D surface. And this can be considered as kind of special case that now the surface is not any kind of random surface, but just the unit sphere. So for those kind of cases, how we can find the basis function is the basic idea of the speaker, the harmonics. So if we skip some details in terms of how we can exactly compute the eigenfunctions, functions, so it turns out that the output of the eigenfunctions is basically defined like this. So the thing is that the eigenfunctions are now defined with the two parameters, two integer parameters. So one is basically the parameter which is called that the order, and the other one is basically degree. So basically what we can see here is that the order is kind of some kind of the quantity, which is basically related to the frequency. So as the order increases, we are basically getting the basis function with some higher frequency, some of the quantities there. And for each of the order, we are basically having the 2L plus 1 number of some kind of basis function. For each of the order, we are basically having this number of some basis functions. So these are basically the speaker, the harmonics that we are getting. So if we see some details here, so these are some examples of some basis the function, the speaker, the harmonics for each of the L and the M, and also these are the visualization. So this one, the first one is basically with when the L is 0, and the second one is when the L is 1, and the third one is with L is 2, and so on. So as we basically increase the number of the order, we are getting some more number of the basis functions, basically the speaker, the harmonics. So by taking these kind of the basis function, taking this set of the basis function, we can also approximate any function defined over the unit sphere as kind of linear combination of these basis function. So the two ways that we can basically approximate the function defined over the sphere is basically sampling over the spatial domain, over directly over the sphere, and basically encoding the values for each of the samples. And the other way around is that now we are sampling this basis function. Typically, we are going to take some kind of the low frequency the basis function, and then calculating the coefficients in a way that we can approximate the function defined over the unit sphere. And the second way can be especially better when we know that the function that we want to approximate is a smooth function, because we are going to use some kind of some low frequency functions. So that's the basic idea in terms of like how we are going to basically discretize the function defined over the unit sphere. Any questions on this? So basically, this framework that what we are going to do is that for each of the corner points, we can directly take out the opacity value and basically take the linear interpolation of these opacity values. And for the radiance, that what we can do is that we are going to basically encode all the coefficients of the speaker, the harmonics, up to the order of the 2. So here one quick question is that if we are taking all the speaker, the harmonics from the order from the 0 to 2, then how many speaker, the harmonics do we get? How many speaker the harmonics do we get if we take the speaker harmonics from the order from the 0 to 2? Yeah, so we are taking the speaker harmonics from here to here, from 0 to 1, 0, 1, 2. So you can see that we are taking 1, 3, 5. So in total, we are taking 5 basis function, right? So which means that we will need to basically store the coefficients of the 9 basis function, right? Yeah. So once we basically store the coefficients of all the 9 basis function, given the view direction, we can basically evaluate the radius function, which is represented as the linear combination of the 9 basis function, which means that we can calculate the radius value for each of the corner points based on the 9 the coefficients of the basis function. And then based on that, we can also interpolate the radius values. So that's the very simple the idea in terms of like how we can run the NeRF without the neural net, but basically by encoding some kind of the information for each of the corner points of the 3D grid. So this is the basic idea of the NeRF-free the neural net free the NeRF the training. Any question on this? So as you can see, even without using the implicit function, the neural network, actually by directly using the voxel representation, actually we can get some quite good results in terms of reconstructing 3D scenes. As you can see, there is no big difference with some kind of the case that we are running the NeRF. But it turns out that the optimization becomes way faster. So typically, when you use the PlanVoxel idea, like when you use the voxel representation, we can basically speed up the optimization like 100 times faster. So this is good. What would be the downside of using the voxel representation? Any thoughts? Like what would be the downsides of like using this idea? Yeah, obviously there might be some basically the trade-off between the resolution and the quality. So as we basically decrease the resolution, then also we may not take some kind of the much the memory, then also the quality of the output will get worse. So if we want to get some really good quality, then we also need to increase the resolution of the voxels. As the PlanVoxel also uses like 512 cubic the voxels, which means that it will take way more the memory. So that's kind of the problem. So this is like the one example. This is not all the cases, but for this specific example, like one specific example, NeRF used only the 2.5 the megabytes, while the PlanVoxel uses like more than 150 the megabytes. So it is taking lots of the memory. So here also the question is that how we can also reduce the memory the consumption in this kind of the idea. So that's also the idea of the instant NGP. So this is also very famous work. So now we are having the two extreme case. Like one is the case that we are having the single MLP that encodes the entire scene, right? And the PlanVoxel is the case that we are not using the neural network at all, but store all the opacity and the radius information for each of the voxel. And the pros and the cons that we could see is that the NLP, the NeRF was the case that we are having some very slow speed, but also having some very compact the representation for the entire scene. PlanVoxel was the opposite. Basically, the optimization and the rendering becomes like way faster, but it is also taking lots of the memory. So how we can make some kind of the hybrid version between these two? So that's the basic idea that we are going to discuss here. So kind of there are also lots of the way that we are making some kind of the hybrid representation. But one thing that we can do here is that now we are storing not directly the opacity and the radius information, but now we are storing the feature for each of the voxels. So instead of like directly storing the radius and the opacity, now we are storing some kind of feature vector for each of the voxels, and then decoding this feature vector using the small MLP. So basically, these are the case that we are using both. So we are using both the voxel representation and also the MLP as well. But the thing is that now we can make this MLP much smaller because we are spreading the feature vectors over the entire space. So here the idea that what we are going to do is that in the NeRF case, we had a single kind of the MLP network that encodes all the entire the 3D scene information. And now what we are going to do is that we are taking out the most of the parts of the neuron, the parameters, and then replacing the most of the part of the neural net as kind of the feature vectors for each of the voxels. So these are now can be considered as kind of the parameters which are basically spatially aligned with each of the regions. So the limitation of the single MLP was that even when you basically update every single point in the 3D space, the whole parameters of the MLP needs to be basically updated, right? Because the single MLP is basically representing the entire scene. But the good thing is that if we basically take out the most of the parts of the parameters of the neural network, and then basically have the features for each of the voxels, if we basically want to update some of the regions, some specific regions in the 3D space, then we just need to update the features that are basically associated with that specific region. So this is not the case that we are basically updating the entire scene, but basically allocating all the parameters for each of the region in a way that these kind of feature vectors can be kind of like dedicated to basically represent each of the local region. So that's basically the idea that we are basically spreading out the most of the neural network parameters, taking out the most of the neural network parameters to basically somehow have some kind of the features that are basically associated with some of the local regions. So that's the basic idea of this, like making the hybrid version. Then now still this can take the advantage of the some kind of the voxel representation in terms of the optimization, and the rendering becomes like way more faster. And still this can be slightly more efficient and then the plan-voxel representation, because we are not directly encoding the opacity and the radiance values, but still we are just having the feature vectors that will be decoded using this kind of quantity, using the small d NLP. So that's kind of the idea in terms of making some sort of the hybrid version. So if we go back to this slide, what we can see is that we are having some voxel grid now, where we are basically encoding the feature vectors, and each of the feature vectors are basically processed using the very small d NLP with some kind of the interpolation. So exactly what we can do is that here, yeah. So we first basically interpolate the feature vectors coming from all the corner points, and then we are feeding this information into the small MLP. And also the thing is that we are also feeding the view direction information here in a way that we can also get some kind of the opacity values depending on the view direction, and then basically predicting the opacity and the radiance using the very small MLP. And here the key idea is that we are making this MLP, so kind of doing some kind of post-processing as kind of like small as possible, in a way that we can make some kind of the more memory efficient architecture. So this is like one specific example that we are having some voxel representation with the 128 resolution, which is now smaller than the 512 resolution, right? So with this resolution, we are encoding the 16-dimensional vectors for each of the corner points of the 3D grid, and we are having this small d NLP that can process the feature vectors in this kind of the later part of the framework. And with this, we can now get some quite good results of the rendering with some much faster the optimization time here. So we can reduce the computation time, the optimization time much more than the NeRF, while basically getting some kind of almost the same output. But the downside is that still we are taking lots of the memory. So in the NeRF case, we only took the more than 400,000 parameters for the single d MLP. And when you basically now have this architecture, the scale of the MLP becomes like much smaller in terms of that we are now only having the 10,000 parameters for the MLP. So here. So compared to this was the case that we are taking more than 100,000 parameters for the MLP. And now we are having only the 10,000 parameters for the MLP, which means that making much smaller the network. But while we are taking lots of the space to store the feature vectors for each of the corner points of the grid, which is more than 30 million, which is much bigger the size. So how we can further reduce the size of the parameters? So the idea for that is basically using the multi-resolution. So here the basic idea is that there might be some areas that we really need to encode some fine details, but there might be some other areas that we don't need to encode some kind of the fine details. Obviously, in the 3D objects and 3D scenes, there might be some kind of the lots of the empty space. So here the question is that how we can basically allocate all the parameters that we are having into some kind of the different resolution of the 3D space. So that's the basic idea. So for that, what we can do is that now we can use not only a single grid, but multiple grid with the different resolution. So we are having the 8 grids, which is having the resolution from the 16 cubic to the 173 the cubic the resolution. So some grids are basically much coarser the grid, and the other degrees are much the denser grid. For each of the grid, now we are having the very small dimensional features for each of the corner points. So now we are only having the 2 dimensions of the feature, the vectors for each of the corner points. But the thing is that now we are taking out the feature vectors from all the 8 grid from the kind of the pixels in the 8 grids. So it turns out that at the end we are still getting the 2 times 8, the 16 times of the feature, the vectors for each of the point in the 3D space. So that's the basic idea. Then we can use the same the MLP the architectures, taking the feature vectors with the same dimension. So here the basic idea is that so if we see like this example, let's say like this is like the voxel coming from the first grid, and for each of the query point, we are basically so locating the voxel in the first grid and interpolating the feature vectors and taking the 2-dimensional features here. And we can also do the same thing for the second grid as well. For the second grid, we are also finding the voxel that includes the corner points, and also interpolating the feature vectors in a way that we can get another 2-dimensional feature vectors. So we can repeat those things for all the 8 grids, and then making the 16-dimensional feature vectors, and then we can feed this into the MLP. So this can be more efficient, the framework, in terms of that we are spreading over the feature vectors into some higher the resolution, the kind of things, and also the low resolution kind of information. So using this idea, what we can do is that, this is the output that when we use the multi-resolution degrees. And now you can see that the quality of the output is even slightly better, while the computation time is almost the same. But now you can see that the number of the parameters that we are using for the feature vectors is the half of the case that we are using the single resolution, right? So in the single resolution, the number of the parameters that we are using for the feature vectors was more than 30 million parameters, while the case that we are using the multi-grid is the case that we are reducing the parameters for the feature vectors into the half. But still, we are getting almost the same quality of the outputs, also almost the same the training time. So this is the basic idea for the multi-resolution. Any question on this? Yes. Yeah. So actually, here the one more thing is that can you further decrease the number of the parameters? So these are all the ideas in terms of how we can reduce the number of the parameters while we are still using the voxel representation, right? So one kind of some sort of the engineering way that we can reduce the number of the parameters using the hash table, the idea. So here, basically what we want to do is that, let's say like the n is the number of the corner points for each of the single the grid. And let's say like we are having the t number of the feature vectors. And we want to just like assign, like we're having the array of the feature vectors here. And we want to basically assign the feature vectors that we are having in this given set in the array into each of the corner points in the single grid. Which means that like if the number of the feature vectors is like is larger than number of the corner points, then we can basically do some kind of the one-to-one mapping. We can basically assign each feature vector into one of the corner point, right? But now, we want to do some kind of the compression, right? So we want to basically decrease the number of the feature vectors even lower than the number of the corner points. So here the question is that even when you basically decrease the number of the feature vectors lower than basically the number of the corner points, whether still this framework would still work. So what we can do is that we are basically just like decreasing the feature vectors in a way that now even we are assigning a feature vector into not a single corner points, but actually into the multiple corner points. So in the hash table, this might be basically the case that we are seeing some kind of the hash collision, which means that like every single the point, the vector actually can be assigned not into the single the corner point, but into the multiple the corner points. But still, would this still work? Like no, which means that if every single the point has the same the feature vector, then that will basically result in the same the outputs, right? Then no, how can you basically handle this kind of situation? So here the question is that now we are basically wanting to like assigning a single the feature vector into the multiple the corner points in the grid. Then this will be the case that we are basically getting the same the feature the vectors, some different the corner points, and this will actually result in the case that we are actually getting the same the output the values for different the corner points. Then how can you handle this kind of situation? Yeah, some positional encoding is actually one of the example, the idea. We can actually feed not only the feature vector, but also some kind of some positional encoding information, like the coordinates of the point and also the view direction. So this will also make some kind of the difference in the some sort of the MLP part. That's true. And also the thing is that now we are also using the multi-resolution grid, which means that even when you basically assign the same feature vector into the different the corner points, when you basically get some kind of linear interpolation of the feature vectors, actually, from the other resolution grid, actually we're gonna get some different feature vectors. We are not gonna basically repeat the same feature vectors for the same, the corner points of the different kind of degrees. So since we are basically using the multi-resolution degrees, when you see the combinations of the feature vectors from all the different resolutions of the grid, actually we're gonna still get some kind of the different feature vectors, and this will be somehow handled in the MLP prediction. So there's kind of some engineering the way that in terms of like how we can reduce the number of the feature vectors while basically getting some kind of the good quality of the outputs, and also still basically boosting the optimization the time, using some kind of the hashing the table, the idea, which does not guarantee, which there is basically no guarantee in terms of like whether we can get some kind of good quality of the output using this idea. But empirically, even when we basically repeat the same feature vectors across the different corner points, since we are using the multi-grid, if the repeating pattern is basically not making some kind of problem, then we're gonna still see some kind of the good results like this. So this is now the case that we are using this kind of the hash table, the idea, which is basically reducing the number of the parameters into the 1/30th like this, having some much smaller the number of the parameters, while basically achieving almost the same quality of the rendering like this, and also the almost the same the computation time, which is slightly taking longer time, but also basically achieving some very faster the computation the optimization, while basically getting some almost the same quality of the outputs. And this is the case that we are taking some more the number of the parameters. Then the number of the parameters is increased, and also the quality is slightly increased. So this was basically some kind of the engineering the way in terms of like how we can reduce the number of the parameters while basically making the optimization be much faster, and also using the voxel representation. So these are basically some of the outputs that you can get as kind of the reconstruction when you basically run the instant HGP. So like instant time, you can get almost the perfect reconstruction results, which is really, really fast. Really faster than the things that you implemented in OSAMA 2. Right? So this was kind of the engineering way in terms of basically reducing the number of the parameters in some voxel-based representation. And here the another question is that whether there will be some kind of some more algebraic way to compress the feature vectors within the 3D voxels. So that's kind of the last idea that we are supposed to actually discuss today, the TensorRF. We're going to continue this discussion the next Monday. And after basically discussing all the some kind of the hybrid representation for the inert, we are going to move on to the generation, the topics. Any questions on this? Is everything clear? So if you have any other questions, please also post the questions on the questions channel on this slide. Then I will see you on Monday. Bye.